All right, let's take a look at some examples of first-order linear differential equations. So, just to remind you, first-order linear equations, we're starting with something that looks like this. 1 times dy dt plus p of t times y equals some other function g of t. And we end up with a solution that looks something crazy like this. So, here we go. Let's start with this one here. Y prime minus 2y equals t squared e to the 2t. Okay, notice this is linear because the y and the y prime are just to the first power. You got something, you got a 1 times the y prime and a something times y and some other function over here. This is not linear, but that's irrelevant from the point of view of what makes it a first order linear equation, right? This stuff. Now, because I already have a 1 in front of the y prime, then I can just calculate what the integrating factor is. And the integrating factor is e to the integral of whatever is in front of the y. And what's in front of the y is a negative 2. So e to the integral of negative 2 dt. And of course that integrates to negative 2t, so I get e to the negative 2t is my integrating factor. If I multiply both sides of that equation now by that integrating factor, I've got the e to the negative 2. Of course, it distributes on this side, right? So e to the negative 2t times y prime minus 2 e to the negative 2ty equals all this stuff that's already over there times e to the negative 2t. Notice, right, this is the derivative, this left-hand side. That's why we chose this integrating factor. It makes the left-hand side the derivative of a product, y times the integrating factor, right? There is the integrating factor times y prime, and there's y, and this is the derivative of that integrating factor, right? If you take the derivative of e to the negative 2t, there's a chain rule that pops in, you get e to the negative 2t times negative 2, and there it is, okay? So the left-hand side is the derivative of this product. The right-hand side, notice there's some simplifying that happens, that the e to the 2t and e to the minus 2t cancel out. You're just left with a t squared there. All right. Now, so the left, sorry, I have a little bit of noise going on in the background. I don't know if you can hear it. My wife is talking to somebody over in the kitchen. And yeah, this working from home thing. As fun as it is, it's sometimes distracting. So let's keep going. The left-hand side was, by design, the derivative of y times the integrating factor, and the right-hand side just became a t squared. So now when I integrate both sides, the left-hand side is the integral of the derivative of this product, and so we just get that product, right? And the right-hand side, right? Notice in the formula, the right-hand side looks kind of crazy. It looks like the integral of g of t times e to the integral of p of t dt dt. It's like, what? It looks crazy weird. But in practice, it isn't necessarily crazy weird that when you multiply the g times the integrating factor, it came out to be something nice. So this integral is just the integral of t squared. I can do the integral of t squared. It's t cubed over 3 plus a constant. Okay, so the left-hand side is nice because it's just y times the integrating factor. And the right-hand side is nice in this case because it's just t cubed over 3. Now I can divide both sides by e to the minus 2t or multiply both sides by e to the 2t, positive 2t, and I get this. And there is my general solution to that first order differential equation. So this equation right here, all the solutions look like this for just different values of c. If I had an initial condition, I could plug them in and figure out what c I want. Okay. There's example number 1. Now let's do another one. Okay, so here's my differential equation. T times y prime plus t plus, what is this? The quantity t plus 1 times y equals t. Also, in this case, I want initial condition that when x is log 2, y is equal to 1. And for whatever reason, I'm grabbing this out of the book. It's problem number 12 in the book. They want t to be positive. The reason this is that we state this is that because it's written this way, there's an issue with t equals 0. Right? I'm going to divide everything here by t, and it's going to turn into a 0 here. And there's a theorem that we'll get to, the existence and uniqueness theorem, which states when should we expect to find a solution. And we should expect to find solutions when we are in an interval where essentially all the functions involved are continuous, right? So this function right here, t plus 1 over t, is not continuous at 0. And so I have to decide, I've got to be on one side of 0 or the other side of 0. Since my initial condition has an x coordinate that's positive, sorry, t coordinates that positive, x equals t, right? I'm saying be on that side of 0, be on the positive side. So anyway, it doesn't affect my calculating that much, but the reason that it's there is because of when I expect to find a solution. Okay. So by dividing by t, both sides by t, I get a 1 in front of the y prime, and I get this as my, as my p of t, and the t divided by t is just 1. That's the g over there. Okay. Now, the integrating factor is e to the integral of this thing, so right here. I'm going to distribute the divided by t in there to write it this way so that I can integrate it more easily. The integral of 1 is t, and the integral of 1 over t is log t. Again, I don't worry about the plus c because I don't need all of the integrating factors that would work. I just need one of them. And so I'll just choose t is, plus 0. And then I'm going to simplify this. So the e to the t plus log t is e to the t times e to the log t. Usually we're going the other way. If you're multiplying two things with the same base, you add the exponents. So I'm going the other way now. That's a product. And let's see, e to the log t is just t. So there's the t, and there's the e to the t going there. So my integrating factor is t e to the t. So I'm going to multiply both sides of this equation by t e to the t. So, oh, but I don't, actually, I'm skipping a whole bunch of steps, right? That is, in this one right here, I'm going to skip a whole bunch of steps because it works out the same way every time. When you multiply the left-hand side by the integrating factor, the left-hand side becomes the derivative of y times the integrating factor. And when you integrate that, you get y times the integrating factor. So every single time you do one of these things, you multiply both sides, you integrate, that left-hand side becomes y times the integrating factor. So that's what I'm writing down, y times the integrating factor. What's it equal to? Well, it's equal to the right-hand side times the integrating factor. Integrate it. Well, in this case, the right-hand side is 1 times the integrating factor. It's just this thing. So the integral of 1 times this on the right-hand side. And this would take integration by parts. I didn't write it out here, but integration by parts, I'd let u equals t, dv equals e to the t. So with u equal t, du is dt, and integrate the e to the t to get e to the t for the v. Anyway, do integration by parts, and you get the integral on that side. Okay. This side right here, who knows what the integral is going to be. Whatever it is, you got to deal with it, right? It might be a u substitution or a trig substitution or integration by parts. Whatever it is, you just have to do it, right? Whatever you learned in Calc 2 is going to be important here. Anyway, integrated by parts to get this. Now I can solve for y by dividing by that stuff right there. And it looks like this, which I opted to distribute and simplify. So this divided by that is 1, and this divided by that is minus 1 over t, and then the c divided by that stuff. Okay. At this point, I can plug in my initial condition. My initial condition was just off the screen there, right? When t was log 2, y was equal to 1. So I'm plugging in a 1 for the y, and a log 2 for the t. So right here and here. The e to the log 2 is just 2. That's that right there. What did I do? Subtracted the 1s, those canceled out, moved this thing over to the other side, and I get this. Now I'm going to multiply both sides by this denominator, I guess, and the log 2's will cancel out, and I get that c is equal to 2. So my solution for this problem is that y is equal to this with a 2 plugged in for c, or written this way, either way. This function, y equals this thing, satisfies the differential equation, and it satisfies the initial condition. It is the solution to the initial value problem. Okay. So here's 2 examples of solving first-order linears. You should try more. there's ones from the book. There's also ones in the title section down below. No, there's a bunch of problems here just below this on the WAMAP page.